All right, so I kind of want to take a step back. We got up to here last time. I don't know where I put my sheet that I was actually working with. But we might go through these real quick again, just in case you weren't here, so everybody has the full sheet. Just to go back for a minute. So the whole idea behind this is if you have a claim that you want to make about something, it's a mathematical claim. So we had an example like if you create a new drug that's supposed to alleviate headache pain or something, or a cream that's supposed to make your cell phone stop turning on, then you want to see if your claim is it's going to work faster than what's available, then there's got to be something you're working against. When you make a claim, it's inherently you're trying to prove that it's not something else. So if I say it works faster, I'm working against the idea that it works.
Or just average.
Well, either. So if I'm trying to say it works faster, so let's say I think my drug works faster than 10 minutes, so it takes less than 10 minutes, right? Then I'm working against the idea that it takes at least 10 minutes. Those two are opposite statements, right? And these are the hypothesis statements. So who remembers which place this would go in for my claim? Where would that go?
The alternate?
Yes, this guy. This one, the null hypothesis, or more colloquially known as the HO, has to always have the possibility of equals. So in the picture, there is what I do is this. I say, all right, okay. Assuming that you're right, that my drug takes 10 minutes, just like the old drug does. You guys with me? And you've heard people say this, assuming you're right. Look at that. Holy shit. It's like evidence. Assume you're right. How the hell is that happening? You with me? It's like, I never burned the spaghetti and the pasta, or overcooked the pasta. I'm like, well, look, you're overcooking the pasta. So it's assuming you're right, then what's happening should be really unlikely. This kind of thing. We've heard this kind of thing. Maybe even said better than what I just did, but it's freaking so. I'll say, assuming that my drug does take 10 minutes, where would a sample have to show up? So if I had a sample that shows up right here, whatever that is, that close, is that evidence that the real mean is less than 10? That's evidence that the sample mean is less than 10. You guys semi with me? So let's say just to give us another number, let's say the standard deviation is a minute. And let's say I take a sample and I get 9.6 minutes. Is that even a full step down? What would a full step down be? And that's not even that far away. One standard deviation is not considered far away. You guys, this is the idea behind all the math that we do, and the idea is actually not difficult to understand. I'm working against it being 10. So I want to find a sample. What I want to do, so this is, you guys agree with me that that's definitely too close. Even 9 would be too close, because that's only one standard deviation down. Let me make sure you guys understand that's like the new standard deviation. That's only one standard deviation down. What if I got 3 minutes? Is that pretty far away? Shit, yeah. If standard deviation is 1, that's 7 standard deviations down. That is obviously far enough away. Do you guys get a feel for this? There's got to be some dividing line between far enough away to be obvious evidence or not far enough away. That's what all this boils down to. That's what a hypothesis test is all about. Setting up what far enough away is. Does anybody remember what part of the problem sets up how far away enough is? That's a really neat phrase. How far away is far away enough? I don't know. What's the restraining order say? No restraining order. So, does anyone remember what that is? Like back in chapter 5, unusual would start at 2 standard deviations away for everything in the universe. But even back then, I think I said that that's not good enough. If I was in a nuclear power plant, I'm not going to wait until the readings are 2 standard deviations off from normal. You guys with me? Yes? I don't know what you would be like in a power plant, but I'm like, I don't know about this. I'm going to get off my ass the minute that little thing starts to approach the yellow. Maybe it's 0.5 standard deviations away. I'm like, what the shit's going on? Maybe. You guys understand? So I really want you. We can't just say 2 standard deviations away is where we start to get concerned for everything in the world. There's some things that don't matter, and then there's some where everybody will die. So it's for everything in between, there's got to be some idea of what far enough away is, and that is the alpha they give me. So let's say somebody gave me an alpha of 0.05. Let me kind of fill this in a bit. So we said that this goes here. This goes here. Why does this go here? Because there's an equal sign. So the null hypothesis is the one that I cannot show evidence for. The alternate is the one I can show evidence for. So a sample can never prove that the mean equals something. But a sample can show evidence that it's not equal to something somehow. So where the tail is going to be is always going to depend on what this dude here says. Where's the tail going to be? Where's my sample got to show up to show evidence? What side? Which side? Left. Okay. And where's alpha in this picture? What's alpha mean? What's that? What's the Greek letter what? Yeah, it's area. Greek letter A. The area where? In the tail, because that's it looks like a fish. It's the Greek letter A for area, and it's got a tail. Holy shit! You're gonna love that. So what's it stand for? The area in the tail or tails. If there's 2, right? We have some mutant fish with a couple tails. Because I didn't get off my ass for the nuclear power plant. Now we got mutant fish. So this is 5%. All right. So let me ask you this. This really is it. If the mean is really 10 of my new drug, what percent of the time would I find a sample here? If that really is the right mean, what percent of the time would I get a sample here? 5%. Why? Because there's 5% of the data in there. You guys see that? Is 5% a very likely thing? So what's more likely? That I just happened to collect people that responded well to my medication? Or that the mean really is in a different place for my drug? Which one's more likely? And yeah, it's a little subjective, isn't it? Maybe it is a little bit, but 5% is pretty damn low. What's more likely is that the picture probably actually looks like this. Let me pull out some color. Are you even working? Let's see if you work. Yeah. The picture actually looks like this maybe, where the mean is lower. Then how unlikely would the sample be? Not very unlikely. It would be closer to the mean if the whole thing moved down. So the whole idea here is the picture for my drug the same as the picture for the old drug? I'm fighting against that. So if I say, okay, assuming my picture is the same, assuming the middle of my picture is the same as the middle of the old picture, 10. Look what I just did. I just did something really unlikely, assuming that's true. So what's more likely? That's not true. That it really is less. And then I can go on TV and say it's been clinically shown that my drug works faster. And that's what it means. That's what it means to say clinically proven. They shouldn't even say proven, but the clinically sort of inherently means we didn't really prove it, we just found evidence. But people won't know that. Now you guys do. So next time you hear a commercial about clinically proven, you're like, All right, you found strong evidence. Okay, whatever. Maybe. So, yes, there are 5 steps to this crazy ass thing. Yes, we've only made through 3 of it in one problem. Because we're starting on, so first of all, we talked about. So, it's going to take us a while. Right? But each step is old news. The only real new step is the end. So let's see. Let's come back to this. Let's remember, you guys have this paper. Let me catch up to you again because I lost mine where we did some work. And for those of you that missed last time, everybody has this, right? Anybody need this sheet? Coyotes? Everybody's got it. Okay. So really quickly. Oh, and I forgot. I changed these around because I was quickly changing this bad boy. What was it? 10.15. So we think that coyotes that live in captivity, we believe that they live longer in captivity. And I had this turned around to begin with, and I forgot to turn the numbers around. So the claim is they live longer in captivity. Longer than what? I'm sorry. I even changed it more than I remember. They live longer in captivity if they're given more room. That's the key. So if they're given more room, they live longer. So how long do they live in captivity, period? 10.15. 10.15 years. So my claim is that they live longer if they're given more room. So what is that in Mathish?
Greater than.
Greater than, lives longer than
10.
All the other coyotes. Rockets. So where's that go? That claim that I just wrote. What does it go in for? It could be either one. But it's specifically one of them because of something it's missing. Which one does it go in for? Which old man in the coffee shop thinks this is true? Huh?
Alternate.
Yes, the alternate, the high. So what's the hope?
Less.
Less than.
Oops, that's 1.5. Okay. So I have a claim. If my claim was, I think it equals this, my claim would go in for the null hypothesis. So the claim could be either one. Since my claim is the high, then I eventually want to show evidence that he's wrong. Does that make sense? Since my claim is the alternate hypothesis, I want to find evidence that the null is wrong. I want to find evidence that my claim is right. Okay, I like it. So again, you can't show evidence that something equals something, but I can find evidence that it doesn't equal that. So I can reject the null hypothesis. If I get so far away from 10.15, then I can say it looks like that's wrong. Yes, Ruben?
How do you tell if it's a one-tail or two-tail test?
Ah, beautiful. What's this going to be? This is going to be how many tail test?
One.
One tail. Why?
Because we're not in between two.
Yeah, greater than is strictly one direction. So when is it going to be two tail? If my claim was, I think the mean has changed. What does changed mean? Does that mean higher or lower? It's a trick question. Changed means either. So how many tail tests would that be? Two tail, because then I can go either direction and find evidence. So here, look at the high. The high is the one I can find evidence in support of. Greater than is the only way that would show evidence, right? Yeah, okay. I like it. So if I took a sample of coyotes and I found they live not as long, they live less, I'm not even going to do the test. I'm dead in the water. I can't even do the test. So this is definitely a one-tail test. Why is it we could use z-scores? Two things. Which standard deviation? That's the key. Population standard deviation is known. If you ever catch yourself saying the standard deviation, no, that's not good enough because there's two kinds. That is what tells me T or Z is which kind I'm working with. What else should I say actually first?
N is greater than.
Yeah, N is 41. So it's greater than 30. So essential limit theorem says, go ahead, have fun. So this part says it's normal enough. And this part says I can use z-scores. Okay, I like it. And again, use z-scores to do what? Define what far enough away is. If I didn't know the population standard deviation and I only knew the sample one, then I'd have to use, if I only knew S, I'd have to use t-scores. But they would do the same thing. They just make it harder to pass the test because they don't have the right standard deviation. It should be harder to pass the test. Okay, so what do we know? We know it's a one-tail test. We gather together everything we know. I know I can use z-scores, and I know alpha is 0.01. So what, did I say t-score? Z-score. So what's the z-score that would go here? One tail, 0.01. I don't even know if I brought myself a t-score chart. Yeah, I did. And now you can see why this t-score chart set up beautifully. One tail test. I'm looking here. One tail test. Alpha is 0.01. Bam. I want a z-score, so I'm just not gonna stop. Bam. If you stop, you get a t-score. If you don't stop, you get a z-score. So 2.326. Why is it positive when I put it here? Because it's above the mean, yeah. Just to let you know, if your tail was on the other side, you better put that down as negative, because we're the humans. We know if it's negative or positive. A piece of paper doesn't tell me which one. It's going, you're the human, you figure that shit out. All right, that's what the paper's thinking. I know it. I love some of you guys. You look at me like, I think he does think that. Okay. So what the shit does this mean? What this means is, and again, it goes right back to the same thing. We just made it more specific. Here's the 10.15, right there, right in the middle. We're going to assume that it really is the real mean for the coyotes that have more room. And we think that they live longer. But if I just find a sample that's right here, that doesn't mean shit. That could have happened by random fluctuations. Whenever I take a sample, is it going to be the real mean? No. So not only does my sample have to live longer, they have to live longer enough. They have to live, their standard deviations have to be more than 2.326 away to be evidence. And there's still, what chance is there? If I do find a sample in here, what does that mean? Let me start there. If I found a sample in here, what does that mean about the null? It seems like it's false, right? The null dude thinks it's in here. He thinks it might be equal to. So if I find something in here, it looks like the null is false, which means it looks like the alternate is true. So the official language we use is, so if I say if z star is going to be the z we calculate later. If that is greater than 2.326. So if I am so freaking far away from the 10.15 that I'm fighting against, I think it's more, and I'm way the hell up there, then I can reject the null. Support the alternate. And again, what's the alternate say? Greater than. So if I get in here, I'm hoping to God you guys see how that obviously supports the alternate. He thought it was bigger, and we got way the shit up there. So it looks like that old guy in the coffee shop is right. It's bigger, which means the other guy looks to be wrong. We can reject the null. Support the alternate. really get that. The null is the guy who thinks it's here, right? Because what's the statement say? Less than or equal to. So if I get here, whoever thinks it's over there looks like they're wrong. Whoever thinks it's above looks like they're right. So what if I don't get in there? Then I just fail to do those. That's all. So either I do these or I fail to do these. Okay. So let's see. Now this is going to be really old news here, part D. What do we know from the sample? Help me out. What's the X bar from the sample? I had to change it up there, hopefully, guys. 12.415, right? Right? So these are the counties that live with some more room. They lived on average 12.45 years. What else do we know? We know sigma. Sigma was what? 4.27. I like it. So what's the new standard deviation? Square root of what?
41.
Yeah, there was 41. Let me stop for a second. That's always going to be part of that step, because what do I do to do a hypothesis test? I take a sample. Oh shit, I'm going to have to change the standard deviation then. So real quick, hopefully you guys see why I call this Z star. Do I already have a Z score on the paper? Right there, isn't that a Z score? So I call this Z star just to make it separate. My Z star is the one that, for my sample, this is just the Z star telling me what's far enough away. So real quick, just to make sure you really, even if you don't like football, real quick, we'll side example. Even if you don't like football, if you had a football team and your whole team is slow as shit, do you want at least one person that's fast? You want probably more than one, but let's say you can get one more person. You want them to be fast, so that's the one you're going to send down to the sideline and throw a Hail Mary pass to or whatever. If you have no idea what football is all about, fast is good for somebody, because then you can outrun the other people. So if your whole team is slow, this is going to be a problem, right? Unless you're all tanks. So let's not say. So the coach, you hold a tryout. You're going to have people run so many yard dash, 100-yard dash, all the way across the football field, right? 100-yard dash. You with me? What's going to be evidence that they should get on the team? Well, you're going to set a benchmark, aren't you? You're going to say, well, you got to run that in this much time, right? So if they get past the benchmark, that's evidence they should be on the team. And if they don't get there, that's evidence they should not be on the team. Are you guys with me? Now, to be really fair, you probably let them do it a few times. If you do it just once, they could have stumbled somewhere. There could have been some loose spot on the ground. You see what I'm saying? It wouldn't be fair then if they're really close. So you're going to take a sample of times. Okay. So that 2.326 is the benchmark I set. And if the sample gets there, that's evidence that the alternate is true. If it doesn't make it, sorry, it's not evidence. I fail to reject the null. I fail to support the alternate. So let's see where we got. What do you guys get for this? Somebody, I think, told me. I'm going to have to go back and get the calculators, but sorry?
0.667.
667? That is neat. And now I can make a z-score. So I've got a benchmark z-score, and then I'm going to see my sample z-score to see how it fell. Where did it fall? So I got to know how far away is far away enough, and then of course the very next step should be how freaking far did you make it? Please let that make sense. And you're all like, I want it to. I really do. So now I can just make a z-score. Z-score, the Z formula is always my data. And remember what I said, what got this whole thing started? We assumed this was true. It was 10.15, so it's always going to be minus this guy. We're assuming this is the real mean. So minus 10.15 divided by the new standard deviation, because we're talking about groups. So I've got to use the new standard deviation. And then whatever the hell that is. Let's see. 2.3. 1 point. It's like 3.3 or something.
3.448.
That's not bad. So did we make it or not? Yeah. That sample is way far away from the number I'm fighting against. It got way the hell up here. This is, so put a little star here. This is where we made it, 3.45. In fact, I think I forgot to say what this region is called. What is this region called? A rejection region. So if I make it in there, I reject the null. And again, what's the null think? The null thinks it's this. The null thinks it's in here somewhere. We got there. Bam. I can reject that guy. I found evidence to reject it. So right here I can say reject the ho. Support the high. It looks like I wrote two things, doesn't it? Does it look like I wrote two things? You know, like, you did, man. That's why it looks that way. But isn't, if I say one dude's wrong, am I not also saying the other dude seems to be right? Because they have opposite viewpoints? Yes, no, maybe so? All right. Before I get too far away from this step, here's one other thing. So in this problem, what was alpha? 0.01. That's alpha. Alpha is the area in the tail of my benchmark z-score, right? You guys with me? The benchmark z-score, the what the book calls the critical z-score, the one that defines the rejection region. I know I'm throwing a lot of words at you that are brand new, so sometimes they kind of go, bleh. Rejection region is just that little place that I have to get into to show evidence. That's what the rejection region is. Right? So alpha is the area in that rejection region. Our z-score was 3.45. What's the area that it makes? What's the area of its tail? I don't know why I'm writing so small. Good Lord, Jeff. Write the number 3.45. There you go, buddy. What's the area there? What's the area in his tail? That's an old question. Chapter 6 question. Can you guys find the area above 3.45? You need your z-score chart, so. Don't tell me 0.99 something crazy. That's not above 3.45. So if you look up 3.45, you have to do well with that, of course, to get the area above. 1 minus. So what do you get when you look up 3.45? 0.0003. So then 1 minus that would be 0.9997. Right, wait, what do you mean 0.00? When you look at 3.45, you get 0.99, so let's do that backwards. You get 0.9997. You guys probably did a shortcut. 1 minus that is 0.0003. Okay. All right, this guy is called the p-value. This is one of the least understood things. I'm not saying that you guys are not going to understand it, but it's just misapplied. Like all of statistics is misapplied. What that means is, in fact, our sample was 3.45 standard deviation, so z-score, right? Is that like something that happens a lot? Would you see somebody with a 3.45 z-score height? This person is insanely tall. You with me? 3.5 steps above the mean of all people. Holy crap, this dude's tall. So that by itself tells me this is really unlikely. This is way out there. that p-value tells me specifically that is the probability that we would get a sample where we did, but the mean, the null, is actually right. The mean is actually 10.15. So again, what's more likely, that the mean really is 10.15 and we just randomly happen to get a sample way out here? Or is the mean for coyotes with more room more than 10.15? That's the one that's more obviously probably right. Is there a chance we're wrong? If we say it looks like that the coyotes who have more room live longer, is there a chance we're wrong? Hell yeah, that's life. Shit. That's why I love statistics. Right? That's why some people hate it. They want it to be more than it can be. Tell me what number to pick in the lottery, statistics. It ain't gonna do that shit for you, buddy. That's life. Somebody guys. All right. And again, this is our first problem we've tried. We're going to do this a few more times. So find the p-value. That's 0.0003. If you read journal articles, I'm going to find some real quick while you guys are doing some work later. What they are going to report are the p-values. From what we just did, is a smaller p-value or a larger p-value? Which one is stronger evidence for the alternate hypothesis? Oh shit, this is a loaded question. All kinds of shit. Smaller. Because that means that's a smaller probability that that sample happened just because of randomness instead of because the mean really is, in this case, bigger. So again, it really comes down to, we got a sample so stupid far away. What's more likely? We just happen to randomly do that, or the mean really is bigger? What's more likely is the mean is bigger. So I could go on TV and say, it's been clinically proven that if coyotes are given more room in zoos or wherever they are, they will live longer in captivity. All right, that's what we found. Is there a chance we're wrong? Yeah. But it's a insanely small chance, way less than normal for me. The probability I'm wrong in any given day is definitely more than 0.0003. So that's pretty damn good. Oh shit. All right. So let's, oh, you know it. You know it. This feels like a lot of work already, right? Obviously. We're not done. We got the last one, your favorite, the conclusion. All right, so here's how this goes. So what did we do? We did this, right? We succeeded. We found evidence. So if I don't make it in here,